Okay, I'll start. So welcome. Okay, if this ever works. Okay. Hello, my name is Gennady Rosenthal. You might have seen me around as a Boost contributor, but these days I daylight and moonlight as a software engineer and upsell team in Google. And we bring in Google common C++ libraries to open source. This will be hopefully easy for you, most of you, and I'll make it easy, try to make it easy for you as well, so there won't be a lot of code. Instead, we'll do a little bit of software engineering archaeology. So feel free to ask any questions, and in fact, I probably would appreciate it. We'll have some discussion if it makes sense what we do. So you've heard Titus to announce our release. It's just initial release. I can assure you there will be a lot more. And I might have also had a chance to listen to John's talk yesterday, where he described some of the technical debt shackles we had to break to free these interfaces for you. And technical debt is bane of most established libraries, and Google is no exception. Today I want to tell you the story, and one more worse story we had to fight through to pay this debt. And to make it more relatable, maybe I'll introduce a few key players first. So strings. We're all familiar with it, and it's actually been used from C++ forever. From early on, string classes were present. Maybe a Rugwave string, QString, you know, probably your own string class in the 90s, if you had a chance to program in the 90s. So they all had slightly different interfaces, but essentially present the same idea. Continuous character buffer in memory. Eventually, it's all culminated in a standardization of basic string template with std string and std weight string specializations. So initially, in a standard, there was not a lot about how string should be implemented. So it didn't enforce. There was some, but not much, about enforcing specific implementation of standard string. So the standard library developers were free to do whatever they want. And I've seen a lot of implementation from straightforward, something like this, like character buffer, size, capacity, some kind of growth factor, usually, which probably not a data member, but somewhere in the logic. There were more sophisticated approaches, the two prominent ones, again, probably most know them both, which is cow and SSO. Cow, or copy on write, was an approach which essentially adds a reference count to implementation somewhere. And the idea is that it allows to avoid copying the buffer if you in a copy construction, and only make the copy when you actually need to mutate it. And it works well if you only copy things around, but it has one big disadvantage, exactly that very same reference count, which essentially made this string into a shared pointer to string, and had the same problems as shared pointers, as it needed to increment and decrement the counter on every copy, on every destruction, and Google does a lot of them. And so this, because we do have a very highly multi-threaded applications. And it results in a very significant visible performance overhead. Another alternative, or family alternatives, were based on small string optimization, SSO. So the idea for the small string optimization is that we take the size of the buffer pointer and capacity and maybe string, and utilize the space to actually store the string. So the string class become kind of value class. We can do it for small enough strings. Actually, if string is less than some kind of predefined constant. It all, again, depends on implementation. This is not how it's implemented, but it could be implemented this way, theory. But again, most important for us to know that this is very different from what it was before. The memory layout is different. So these strings had an advantage for small strings, because you don't need to allocate the memory. You actually use less space, less pressure on allocator, and it improves cache locality for you. So this is our two well-known string implementations. One more thing I would like to kind of remind you is inline namespace. Again, as most probably you know this inline namespace is this feature of C++11 which allows us to change the implementation and keep the public name. So in this case, we have function foo in the namespace n. This is its public name, n : foo, while the compiler, when it does its work, will give it different name, which is gonna based on n : _1 : foo. So this allows us to have one public name, and theoretically, which we can change internal name and change implementation. And what most important, we can link together two different implementation to the same function. So you can, this function will, for example, it's build once, then you change your mind and implement it differently, change the inline namespace, and you can build another translation unit with different implementation, and you will be able to link them all together into the same application. It will work. So this is really why we would use inline namespaces. So finally, let me introduce one more key player, which is Application Binary Interface, ABI. So we're going to reiterate on it a little bit later today, but for now, it's easier to think of ABI if we match it against API. So API, Application Programming Interface, is the interface to your library on a source code level, while ABI is interface to your library on machine level, on machine instruction level, where after the compiler built your library, this is how we interface with your library. And it contains usually a lot of details of it's platform specific, but most important for us will be memory layout of your types defined in your library. So classes can have the same API, but different ABI. We just seen it. Cow and SSO std string implemented exactly the same standard, but have a different ABI, different memory layout. Okay, so without further ado, let me tell you the tale of a standard string imposter. So Google has a long history of using C++. It started early, and from forever we are using C++. We started with GCC 295. And at the time, it was use a string which is implemented using some flavor of SSO. Being pre-standard string, pre-C++ 98, GCC 295 actually did not have a namespaces. And string class resided in a global namespace. So it works for Google for some time, and we didn't upgrade for several years until standard settled. But by that time, string class is used all over the place. Now, huge sort of base, which was like 1 million lines of code at the time. So, and starting with GCC 3, it implements C++ 98. And it implements the standard, and it comes with a new string implementation based on copy on write. And it was fashionable at the time, and GCC used that implementation for GCC 3 and GCC 4. So Google wants to move to that new standard library to standard. We were using pre-standard implementation before that. So as far as I can tell, it's around 2003 there was an effort to do that, but the task seemed unfeasible for two reasons. One, we realized that we have this million lines of code and we have no idea how to go and sprinkle std : everywhere. We didn't have the tools. The whole process took a few years going back and forth, but while we're doing that, we also realized we have another problem. The cow string is slower in Google use cases. It's slower by about 2%, which is significant. It's a lot of money in Google for Google. So just because someone wants to make code clean and add std : Google will not gonna do that because 2%. So we were contemplating this for a while, and GCC releases for one and around 2006. And it implements now C++ 3. We really want to move there. and we're still having the same two problems. Standard library is namespace std, our code isn't, and we still have a code-based std string. Our code base is now bigger. It's 10 million lines of code. So we decide eventually, the bite bullet, we will use using declaration. So we have using like std vector somewhere in common place and use that header instead of vector. And that allows us to, not to, so that allows to not to touch our code and switch to a new standard library, almost. We still need to deal with the string, right? That string is not good for us. It's still slower. So what we decide to do is, well, what the heck? We are using global string anyway. We will have our own string. Our own string, which will be much better than standard, which will use a small string optimization. It will implement it, and we'll use that instead of standard string. At the time, it seems like a valid decision. And we actually didn't even implement the whole string. GCC came out with both cow string and SSO string, which was called versus string and resided in X bits. We just redirected most of the implementation to X bits versus string. It ended up with a tiny class, and that's how the standard string imposter was born. For a long while, we lived in an easy peace with this standard string. We learned to hate it. We learned that it cost us, and approximately by 2014, the C++11 came out, and C++11 came out in 11, but by 2014, GCC came out with the corresponding implementation. We were ready to do something, but we still need to do. Okay, I wanted first to tell you what we learned from our experience with this imposter, because we used it for 8 years and we were really ready by 14 to move away from it. But why? First of all, we realized that there's a number of open sourcing efforts. We are trying to open source Google code, and every time someone tried to do it, the string, different spelling of string was a problem. How I can open source this? What I need to support back and forth conversion? That's why we've seen a number of open source just being released once and never touched again after that, because it's just a nightmare to support. Conversion back and forth, one of the reasons at least. We also obtain a number of third-party dependencies, which use standard string as interface. So the dependency was actually using std string, not our string. So when we want to communicate with that library, we had to construct string, operate on string, convert between our global string and std string. So we had a number of interfaces where we have overloads for string, a global string, a std string, or specialization for string and std string, and then conversion between string and std string, just because we needed to satisfy the interface. And that led to performance overhead. We also learned one more thing, that for every new developer which comes on board to Google, every new C++ developer, they need many other things, that many other quirks of Google C++ development. They need to learn, don't use std string, use this string instead. And people slipped, and this resulted in a bunch of unnecessary comparisons, again, conversions, because just std string compiles. It's not that it's not visible. This class is visible. You just shouldn't use it. And once again, to some performance degradation. And on top of all that, by 2014, our code grew to 150 million lines of code. I wanted to give you like one bonus anecdote. So I've learned this while working on preparing our common libraries for release. So as it happens, this comparison worked, but this comparison was never defined. There is no operator comparing std_string and string in Google code, but it worked. And the reason it worked was this is completely separate class called string piece, which is what you know now as upsell string view. So which resided in the global namespace. It looks approximately like this. So this class string piece, it was constructible from implicitly constructible both from std_string and global string, and it resided in the global namespace. And it also has operator equal, which also resided in the global namespace. All of that leads to this comparison working. And as far as I can tell, no one in Google actually realized it. So that was true for all the other operators as well. Until I actually moved string piece into the upsell namespace. And it broke. And it's broke. So that's ADL wonders at work. And one more reminder. Don't define anything in global namespace. It's not your source, it's shared resource. So getting back to our tale. So 2016, upsell team is tasked with open sourcing Google Common Libraries. And we are fed up with a global now a global string. We want to get rid of it. We cannot live with it anymore. We cannot open source our libraries. You would laugh to our face if you'd say, oh, use also this global string also, along with our library. And it also wouldn't be possible for us to do conversion back and forth, right? On the plus side, thankfully to Chandler's team, we now have tools. We have tools, so we actually can go through our, 200 million lines of code, which we had at the time, and actually go and sprinkle std::: everywhere. Well, in a semi-automatical manner. It only took us half a year, I think. But we get there. We pretty much do not have global standard symbols anymore. We have std::: everywhere. But for string, we still need to deal with a string. So what are we going to do with this cow-based std_string? It's still performance hit. So obvious question, can we just go in standard library implementation and just replace it, right? We have a standard library implementation, we can build it. And it's a separate story. I'm not going to, I had, out of the 1.5 years that I've been doing this, I remember I probably spent 8 months trying to move the build system from whatever the standard library has to what we need. But that's separate, unrelated story. But anyway, so can we just go and change the standard library implementation? So obvious answer is no. We still have pre-built third-party dependency. If you just go, don't change the symbol, change the ABI of a class, it will break the first second it hits the third-party dependency which use std_string. They're not going to be memory. There will be different memory layout. It will break. So we cannot change the standard string. So we need to somehow serve two masters. We need the same library, have a std_string which works for the third-party dependency, and we need also the same library had a different SSO-based std_string which will work for Google code. So we did find the solution, but we had to do one concession. We cannot deal with the third-party dependency which has std_string, and in fact, as we can find out later, anything from STL in API. Why? Because even if we magically have these two classes coexisting, we cannot pass it through the API boundary. You cannot take std_string with one memory layout and pass it to the library which expects different memory layout. It's not going to work. So with a little bit of pleading with the various Google teams, I was able to eliminate all of this. Some of them were eliminated, some of them were built from sources, some of them were wrapped into extrinsic APIs, we don't have any more third-party dependency which has standard library in API, pre-built third-party dependency. We still have a third-party dependency which depend on standard library. So now with this out of the way, this is the skeleton of what I did. This is approximately the solution. You can take a look, but this really is not that complicated. So effectively, the same skeleton was done pretty much for every header in a standard library implementation. Well, the only exception is that in this case, this is string. I had two different string implementation. But for everything else, it just conditional adds in line namespace. What I do next, I can build the standard library twice. One with the version symbol undefined, and one with the version symbol macro defined. And I can actually link all of it all together into a single fat standard library. So when version symbol is undefined, we get a symbol which will be used by the third-party dependency. When we build the Google code, we do define the version symbol macro. And as a result, the Google code will use new as a source-based string. And the standard library will include that symbol under the different mangled name, stood Google basic string, and it all resolve. So it's not very pretty, I admit. And our standard library is twice as big, but miracle of all miracles, we have now two standard string inside implemented the same standard library. And thus, this ends the story of our standard string imposter. And the second part of this talk, I'd like to see what lessons we can learn from our tale, from our experience with this. I'll be talking about mistakes, but in really, I'll be talking about mistakes tolerance software design. Well, the word mistakes, it's a little bit misleading. It's not necessarily a mistake. In practice, it could be indeed a mistake in your design or implementation, but it could be also change in requirements. It could be that you didn't have a tool to do some changes at the time, and time passes. It's usually how it goes. With time, you realize your mistake, your requirements changed, or you got a new tool, and you face the need to do some change. It doesn't matter why. And that you need to pay the technical debt. You need to fix a mistake. So lesson number one, I hope we can agree we need to face reality. Mistakes are inevitable. We have seen a few examples in this story. Standard body probably shouldn't have allowed cow-based strings in C++ 98. That's a hindsight, but still, maybe. Yeah, they probably shouldn't have. It probably was not a good idea by GCC to release cow-based string in GCC 3 and 4. And Google could have avoided a lot of headache by investing into tooling sooner and to allow to switch to stub namespace much earlier. It would have probably took a week in around 2003 if we didn't have tools at the time. Now, lesson number two, fail faster. You all know this. The longer it takes to fail, the more expensive it is to fix. This applies to our everyday development. When you develop your code, you want your IDE or whatever you use to show you your typo right away, even before it compiles. And some IDE do this these days. Then you want a compiler to show you a mistake very quickly. We want quick compilers. If it's not compilation, we want linker error. If not linker error, we want some kind of runtime assertion. And the worst mistake we can do is mistake which requires some kind of logic mistake, which requires you debug and spend however long it is needed to debug the code and figure out what's wrong. And finally, lesson number three, probably one of the best advice you can give to the budding library designers. Assume you're gonna get it wrong. This applies to everybody in this room, and me including. And despite how long you do this, it's maybe 1 year or 20 years, despite the best intentions and preparations, sooner or later you realize you got it wrong. So we need to prepare for that. So what does it mean in practice? In practice, if you know mistake is inevitable, you want to design software which is easier to fix. Right? This applies both to mistakes in design and mistakes in implementation. And the second practical consideration is it's always easier to fix a mistake if you don't need to break a contract. Term contract is a little bit, it's not exactly a legal sense, but in software engineering sense. Both your library API and ABI are the contracts between you and your clients. So what kind of contracts we should prefer in mistake-tolerant software design? Let's consider API first. And again, it's not language lawyer view. So API is essentially a set of interfaces exposed by the library, right? So it consists of types, free and public member functions, or maybe a few other things, right? In C++, in ABS and so on. So classes have a guarantee, like string view, for example, can guarantee that it's trivially copyable. And it's possible, it's a valid guarantee. What is missing in this? The fact that class is a class. This is not part of it, and probably should not be a part of your contract. In most cases, we do not want this to be a part of our contract. This allows you to make the mistake, make the change like this, and do not break the contract. You did not promise the class to be a class. And that's exactly the reason why we don't want anyone to forward declare any one of our classes, because we don't promise you that. We did not promise you this is going to be class. We did not promise you that anything really. We promise you the name. And here's the name, foo. So in this case, we introduce an alias, but it might as well be template specialization or a few other things, right? It's all valid if you didn't promise the class being a class. And if you broke someone, it is their responsibility because you did not promise. They broke the contract. Contract for the function essentially defines how it can be invoked, right? What it does. So given these inputs, this function produces outputs and has these side effects. This is contract for the function. Undefined behavior, absence of guarantee, can also be a part of a contract or for the function. For example, standard string construction based on null pointer is undefined behavior. It is part of specification. Specification says this is undefined behavior. This is a contract for this class. Undefined behavior allows you to, if necessary, change in the future and restrict this undefined behavior to something defined, to restrict your side effects, restrict your outputs, and specify the behavior. So, in fact, my advice, undefine your behavior as much as you can afford. It is not your responsibility to worry about users breaking your contract. There are tools for that, and it is not your responsibility. Your responsibility is to define the best contract for your library. Again, what was missing from that discussion with about the function contract? Most commonly, the signature. Sometimes also performance expectations. So again, you don't want to promise anything about the signature. It allows you to change the signature without breaking the contract. For example, in this case, I've added optional parameter, but it might have been like turning the function into function template or turning it to something else. Maybe it can become a lambda. Variations, what it can be. So in summary, in a mistake-tolerant design, promise the least, demand the most. We want the least restrictive contract, the function on the function outputs and the side effects, so that we can so the least restrictive contract for the function outputs and side effects, so that we can restrict it further down the road, and we want most restrictive on inputs, so that we can relax the restrictions later. Right? Let's talk about ABI. So ABI, application binary interface. Again, we're still not going to talk about too deep, because ABI, it's a platform specific, it's a big specification, and there's a lot of going on which involve with how compiler will generate your binary, what it look like. So API, as I said, difference from API because that it defines interface to your library on a binary level. In specification, we'll see it includes like processor instruction set, or it includes sizes, alignments of types. But most important for us is it includes memory layout of your types visible to the user. So what is the memory layout? In most cases, what it is, it's a content of virtual table. Layout is defined, layout of virtual table is defined by ABI, but the content of virtual table is important. And data members and base classes of your class, all of that together defines an ABI memory layout of your class. Note visible to user part. No memory layout of implementation details. For example, if your class uses some kind of pimple, which are hidden in a source file, they do not become part of an ABI. Practically, you don't need to know specifically, like in most cases, unless you optimize the size of the class. And in many cases, you do. But if you're just worrying about ABI, you just need to know that given this set of virtual functions, this set of fields, set of base class, and in their order, this is that defines the memory layout of your class. As soon as you change any of that, it will change. Also, ABI controls the calling conventions, the way how arguments are passed to functions. So it depends on some attributes of the type. For example, if a type is copy constructible. For example, in this case, if you construct object foo and pass it to take foo function, most likely what will happen, it will be passed through register. So it won't just be by value, just passed to register. But if you make the change like this, it will be passed via the pointer. And then pointers will be put to register. You can go if you want to check it on the Godbolt. Finally, mangled name. So mangled name is a unique name compiler generate for your symbols in the library. We all know that. So we know that the class name is not enough. We also have a namespace, but in reality, you also need to know, like function, for example. You need to know type of all the arguments, or maybe it's a template function, also all the template arguments. All of that together somehow produce a unique name. There's a very complicated, well, somewhat complicated rules how this name is generated. There's really two things we need to know about mangled names. First, we need to know that if you change only some implementation details, like for example, you change the order of these fields, the mangled name will not change. And that's why specifically we were not able to just go with standard library and implement it differently, because mangled name didn't change, but memory layout would have changed. And we've got an ODR, one definition rule violation. ODR violation you can find in many scenarios in C++, but ABI breaks in many cases are ODR violations. On the flip side, you can also you need to remember that sometimes some innocent change will change your mangled name, and even without changing the API. And thus will break an existing pre-built code. For example, if we go from this to this, the API, one can say that API didn't change. We just added the variadic, made it variadic. So, but ABI, the mangled name will change. So if you expect some pre-built library not to break, most likely it will. Depends on compilation, the platform, sorry, but most likely it will. So summarizing what I said about the ABI, your library ABI is a brittle flower. There are many ways to break it. I listed some of them here. You can reorder things, change the calling conventions, change your mangle name. So again, in mistake-tolerant software design, undefine your behavior and do not make any ABI promises. You will likely need to break them. So better not to risk it. Instead, you can prepare for the time when you will need to break it. So this is one approach. Well, probably one of the preferable approaches these days, introducing line namespace. So when the time comes and you do need to change ABI, you will change your line namespace. And you will be able to support the situation where you have old library built with your old version of your code and new library of your code, and they will happily coexist inside of the same binary. You prepared for binary break. You can also have an opinion that I don't know anything about ABI or don't support any ABI at all. Effectively build from source. If you had our only library, or even if your source library, you can say, always build me from source. This is essentially upsell view. We want you to build upsell from source. You can, in theory, take upsell, pre-build the library, and link with it once, but don't expect anything. You don't even expect that we, year from now, change, and it will be able to link together with the old version of upsell. We don't promise anything about ABI. If you really, really want to promise ABI stability, in some cases you do, there are a few approaches, essentially which all comes down to make sure that the memory layout visible to the user is stable. And there are a couple well-known ways to do it, using Pimple, using std_any, and various other opaque pointers. Okay, so a few conclusion remarks. Paying technical depth is expensive. It's not cheap. If you can do it, the result will worth it. Even better, remember, mistakes are inevitable, so assume that you are going to get it wrong. Better be prepared. So thank you for listening, and enjoy making and fixing your own mistakes.
I have a question. You showed in the API that you're trying not to promise anything. For example, you gave foo, and then you said using goo equal foo, and now that's still legal because that's
using foo equal goo, I think.
Yeah, using foo equal goo. I'm using foo type. So it's, I mean, it's nice to say, but you can't. You keep the API, but it's going to break compilation because the user now need to build a different type of class. What he used to as foo is a different class now, right? He needs to create.
Foo is an alias, but the existing user code will build perfectly fine. The goo, which is foo is an alias to goo now. Goo is a class, and foo used to be a class. So any statement you had constructing objects of type goo will continue to work.
So if foo and goo have the same.
Yeah, if you've had a chance to see the John talk, he will go in. If not, I recommend you see the slides and maybe video. He go in more details into that, but it will work perfectly fine. That is the recommended way to do some refactorings.
Okay, I think I understand now. Okay.
Hi, great talk. I had a question real quick. So the other solution that you had before you went into the lessons learned, do you consider that solution a hack? And if so, in your ideal world, what would have been your more permanent solution if you could implement it? If that makes sense.
I think, well, it's clearly not ideal, right? The library is twice as big, so there is an overhead. Symbols is longer. There's small overhead on that as well. And ideal solution would have been build everything from source, leave it head, and make everything, all the dependencies, build all the dependencies from source. If you can do it, and I think eventually we will get there, this will be our solution, and we will be able at the time switch to libc++ instead of libc++.
And so your solution is to build libc++ from scratch, from source. Or you say your
We will, no, libc++, we probably will build prop source as well.
Pretend I don't know. So you said a couple times that doing the inline namespace trickery for the standard library required us to double the size of it. Why didn't we just add the new name for string, since that was the only thing that was causing the problem?
This was an original idea. Let's just duplicate string. And it didn't work. Burned. Problem is that the string, the moment you duplicate string, you need to realize that string is everywhere in the standard library. String is every exception type. You duplicate exception type, you need to duplicate the function calling the exception through whatever they call it, hiding exception. And the moment you do that, it goes south from there. You need to duplicate pretty much everything.
It seems that on the slide where you show ways to keep your API stable, there is one option missing, like expose external plain C API to users. So it makes things much simpler. What do you think?
External C ABI just by itself does not mean you have a stable ABI. External C, just like as anything else, if you have a struct and you suddenly change this content of that struct,
Yeah, but that's definitely true. But for example, it's much harder to break it. For example, by changing the order, your class is.
it is somewhat more stable, and that's why, as one of the options, what I dealt with, how I dealt with third-party dependencies was I wrapped it in an external C API. But ultimately, this is not this. Just use an external C and you're good. You still need to be careful, maybe a little bit less overhead work, but still external C will require some work.
I'm curious, how does the inline namespace trick interact with ADL? I mean,
It will work. I mean, what specific?
well, so say like you have like, you know, inline namespace 1 and inline namespace 2 in your namespace, and you have like a function that's in inline namespace 2, and it takes the type that you're using inline namespace 1 with that. Now, like, will they, and you call the function via ADL, does that work?
I would need to double check this. As far as I remember correctly, effectively, you can assume it's not there at all.
The inline namespace, you mean?
Yeah, it will say it is in namespace N in my example. And they will both kind of in an namespace N if you have two inline namespaces.
Hey.
Just another question, just remind, you were using, like, trying to create a new thing called string, like the Google string. Do you think the whole thing would become easier if you would insist on using the name string? I mean, if you would just call your string cow string or something like that, or would just make things harder?
I don't know. No, how we named our global string really doesn't matter much. We could have named it our favorite Google blessed string. it would have still be the same problem. I mean,
And we also had all of the code that was already written in there.
exactly. We already, by the time we were inventing our imposter, we already had a bunch of code, and our problem is that we cannot rewrite it. So if we would want to name this class someone different, that means that we would have to go and everywhere name that string class somehow differently.
So you were already using std string.
We are using not std string, we are using global string.
I've got a question. I was wondering, did you consider attacking the third-party libraries where instead of just editing the header files so that they accepted strings that were of the old form, so that you go through and just remove the std string and make them go, this is the copy on write string on all of the third-party header files where you couldn't.
Also, we're talking about third-party which is pre-built. They have a fixed header, they're pre-built.
Yeah, but you can just change the textual of the headers to be cow string, so that when you pass through the call interface, when people are interacting, then you can get those ones to work.
I'll probably need to think about more details, but even in that scenario, if I understand you correctly, so let's say we go into third-party library header, change the name of, instead of include string, we'll write include strings, then say string is like, I don't know, using.
It's just editing them to be the internal, so it's like the name is the internal name that they're using for the essay build.
I still need to pass the string the library expects. And if I internally use a different string with a different memory layout, at the very least, I will end up with the memory with the conversion.
No, I was saying just you change so the header file, it says std string.
Okay.
And you want that to be the cow string. So just in the header files for the libraries that you can't rebuild, you just change them to the cow string, to the cow string. So
They've already been built with std string being a copy on write string.
Yes, and so you just change all of the header files that refer to them to cow string.
But the binary is already built.
Yeah, so the binary is built with cow string, and so when you interface
Cow
it,
string is
Google will be using.
Change all the manual names in the binary.
Yeah.
oh yes, that's the
Cow
manual.
is one, yeah, and cow is the same number of letters.
Okay, I forgot about the name library. I'm sorry.
Okay.
on the subject of Megalith. This is a bit sharp. You mentioned symbols being longer. So obviously in the Titanium ABI mangling, std string is blessed and has a really short mangling.
Yes, I know. I can talk for. It is an impact. There will. It actually somewhat still work in progress. There is an impact, and indeed there is the compiler has shortcuts for these symbols in the std namespace. Let's say that we'll have to deal with that. This is less of a problem.
Yeah, clearly Google's been paying that cost since forever, since it's never been using std string. So this change presumably didn't make it worse.
Yes.
So back to the changing the header files. So like, could you have like the cow string at like name and
Okay, it
mangle
turns
in the
off.
same like place? And just have it in std string, and then you have your own std string mangled differently. And like, does that make any sense?
You could have our string or Google string instead of an inline namespace in a truly nested namespace.
Yeah.
And they're using declaration, but then like ADL starts to get weird and other things.
Yes. No, this will not work. The ADL will not allow us to do that.
Got it. Okay.
Any more questions, guys? Thank you.
Thanks again.
Thanks a lot.